Alright, so now what we're going to do, now that we've got the idea of what we mean when we talk about particle motion, how do we interpret rates of change, and we looked at an example last time of an algebraic representation of a particle motion problem. Now what we're going to do is we're going to look at an example where we're looking at it from a graphical perspective, where you're going to be given a graph that you're going to use to answer the questions that are given in this problem. Okay. Now the first thing to notice about this problem, and it's really important on the AP, is to know whether or not the graph that they give you is a graph of the position function or the graph of the velocity function. And we're actually going to do two examples, and if you'll notice in example 6 here, I have labeled this as S in inches, so I am being given the position function of the particle. Okay, so that's going to be important for you when you start doing your interpretations. So when I'm talking about the velocity would be the slope of this function. Okay, so we're given S of t. It is a particle that's moving along a horizontal line, which is going to be moving left or moving right. Okay, so now we're going to ask the question, when is the particle moving to the left? And so what we've learned in the last few examples and in the preview for this, that a particle moves to the left, we would consider that to be the negative direction. And so we would say that the particle is moving left when your v of t is negative. All right? And remember that v of t is s prime of t when the derivative is negative, also looking at the slope of the line. So when we're looking at our position function over here, our slope, I'm just going to use m, our slope is 0 on this section. Our slope is less than 0 from 2 to 4. Our slope is bigger than 0 from 4 to 6. And then our slope is again 0 here on the end. So when they're asking when is the particle moving to the left, I'm specifically looking for where the slope is negative, and the slope is negative for this portion of the position function, which corresponds to an interval of 2 to 4. So the particle moves left for time an element of the 2 to 4, and if they ask for a reason, you would say because v of t equal to s prime of t is less than 0. So that would be our answer and our justification. And then likewise, the particle moves right for t on the interval, and so right would be this section of the graph, 4 to 6, 4 to 6, and again our justification would be because v of t, which happens to be s prime of t, is positive, greater than 0. Okay, we might want to include units here, so I'll add seconds after that, so we know we're talking about time from 4 to 6 seconds. Right? Now, when is the particle standing still? That's utilizing the information that the particle stands still when the velocity is equal to 0. It moves right when the velocity is greater than 0, standing still when the velocity equals 0. Okay, and again, we could also refer to this as the derivative because that means the same thing. So we're looking at where s prime of t is equal to 0. And again, remember we're talking about the slope. So I'm looking at on this graph of the position function, where is the slope 0? The slope is 0 for the interval 0 to 2 and for 6 to 7. Now, kind of a comment about brackets versus parentheses here. Usually when we're looking at these, I would probably not worry about including the endpoints on this. We'll talk a little bit more about what might happen on the endpoints, but this is especially because we're only considering the slope. The slope requires kind of an instantaneous rate of change. There really technically is no derivative here at 2 because there's a cusp. There's no derivative at 0 because there's no left side, and there's no derivative here or here because of the cusp, and then no derivative there. So it has no slope, no speed at those points, So the idea is what you're doing is basically saying the open intervals. So for our answer for C, particle stands still, particle stands still for t on the intervals 0 to 2, 0 to 2 seconds, and on the interval from 6 to 7 seconds. 6 to 7 seconds. Right? So that's fairly straightforward in terms of taking a look at our position function and using that to interpret when the particle moves left, moves right, and stands still. Now what we're going to do, this next question starts about our displacement. And if you remember, our displacement is simply our change in position. Okay? So during the first 6 seconds, so this is for an interval of 0 to 6 seconds. For the first 6 seconds, our displacement, by definition, means we're simply going to calculate s of 6 minus s of 0. So we essentially need to use the graph to elicit the information that we need, which is what is the y value when the time is 6. So in looking over here, the y value when the time is 6 is going to be negative 2. And the y value at 0, that's this point up here, your y value at 0 is going to be 4. So we are essentially using the graph to get the y values and then plug them in. So our displacement would be negative 2 minus 4, or negative 6. Now typically we do want to go ahead and interpret this, and so our interpretation, I'll write it right here below, we would say something along the lines of the particle during the first 6 seconds, the particle is displaced 6 units to the left of the starting position. And I know that I'm to the left because my displacement was negative. If my displacement had been positive, then I would have been to the right. Right? Now the second part of this is, what is the distance traveled? And basically you have to kind of be very careful with this and think about what is going on. You basically need to add, for the first 6 seconds, so for my 0 to 6 seconds that we're going to be talking about, I basically need to take the distance that I've traveled left plus the distance that I traveled right. And since I'm doing a distance, it's actually going to be the absolute value of the displacement. So when I'm doing this problem, here from 0 to 2 seconds, I'm standing still. So nothing is happening there. I'm not moving, so there is no distance being traveled. For the interval from 2 to 4, my slope is negative, so I'm traveling to the left. So I'm going to calculate my displacement from 2 to 4, which is going to be s of 4 minus s of 2. But then I'm going to do the absolute value of that because I want it to be a positive distance. I'm looking for the distance that I have traveled. Right? Then we're going to add to that the distance that we've traveled right. So from 4 to 6, I'm traveling right. So I would calculate my displacement from 4 to 6, and technically you would be doing the absolute value for distance, although it's really unnecessary in this problem. So in calculating each of these, our s of 4 is going to be negative 4. Our s of 2 was 4. Right? Then our s of 6 is negative 2. And our s of 4 again is negative 4. Be careful with your negatives. And so we end up with the absolute value of negative 8, or 8, plus negative 2 plus 4, which is 2, and that gives us a total of 10. So the total distance traveled for the first 6 seconds is 10, and let's go figure out some units. Do we have any units? Yeah, inches, 10 inches. And then while I'm thinking of it, this would have been inches here, so let's change that to inches. We have seconds on all those up there. And so you can kind of see the difference between displacement and distance traveled. And again, we're reading the information off of the graph to answer the question. All right, so now we're talking about the particle's velocity at t equal to 5. So there we're utilizing the idea that what you're recognizing is that the particle's velocity at 5 is going to be using the derivative of the position function. So we're basically looking for the slope at t equal to 5, the slope of the tangent line. So up here on my graph, I find 5, that's this point right here, so I really just need to calculate the slope. I know it's a positive slope there, but I need to calculate it. I don't have a formula, so I can't find a formula for the derivative, but since this is a linear position function, the slope is the same and constant for all points, I can really just calculate this doing change in y over change in x. So I would take 2 points on the curve that you definitely know. So I have the 6, -2, and I also have the 4, -4. And so I'm simply going to calculate this by doing change in y over change in x. So I'm going to do my s of 6 minus s of 4 over my 6 minus 4, which is going to simply be my -2 minus -4 over my 6 minus 4, 2. Notice that this top, 6 minus 4, we actually did over here. That was our displacement, which is 2 over 2, which gives us a slope of 1. Now remember, we do want you to interpret this and put units on it. So right now, our units change in y, inches per second. Right? And then let's come in and let's interpret this. So we would say at t equal to 5 seconds, the particle's position is increasing at 1 inch per second. Okay, so notice that even though I'm giving a velocity here, that when you are explaining what's happening or what you just found, this is your when, this is your what, the particle's position is what's changing. Which way is it changing? The particle's position is increasing at the rate of change that it's increasing at. All right, so now we're going to come down here and we're going to take a look at graphing our particle's velocity and the speed, okay, where it's defined. Now remember, we have a function up here on the interval of interest, 0 to 7, it's continuous, however we have cusp. So there will be not differentiable, this position function is not differentiable at 2, 4, and 6. And then of course also at the endpoints because there's no left side. So, but the other nice thing about this and taking a look at the graph is our slopes are constant. Now we already figured out this slope right here. Our slope for in between our 4 and 6 was actually a slope of 1. We know 0 and 0 here, so I'm going to come up because I know I'm going to need it. Let's calculate this slope that's the negative slope. Again, I'm going to do change in y over change in x. So, and I'm just going to go straight to it. So I have -4 minus 4 over my 4 minus 2, -8 over 2. And again, there's my displacement that I already knew, which is -4. And again, remember this is inches per second. So my slope there is -4. So from 0 to 2 seconds, I have a slope of 0. So I'm simply going to go, hey, the slope from 0 to 2 seconds. Notice I'm putting open circles at the end because it's not differentiable at 0 and 2. And then from 2 to 4, we just found that we had a slope of -4. So from 2 to 4, we have a slope of -4. And it's constant the entire time. From 4 to 6, we have a slope of 1. So we add that in. And then from 6 to 7, we again had a slope of 0. So that gives us our velocity position that we're looking at. Now we're going to look at the speed. And remember that speed is the absolute value of the velocity function. So basically all it does is make the velocities all positive because speed is positive. It's only the magnitude. Well, it's not going to change anything here. From 2 to 4, instead of being -4, it's now going to be up here at 4 because while I was heading in the left direction, which is what the negative is telling me, my speed, my magnitude is 4 inches per second. And then from 4 to 6, nothing changes. It'll stay at the 1, and then again here at 0. So again, that's just showing you the relationship between the velocity graph and the speed graph. All right, and then we come down here and then we go, at what time is the particle moving the fastest? Now, when they ask this question, they are referring to speed, because what they're looking at is you could be moving the fastest in the positive direction, or you could be moving the fastest in the negative direction. All right. Now, in this question, you're basically going two ways to look at it. One, you can take a look at your speed graph over here and simply go, well, where is it at a maximum? The maximum speed occurs at 4. So the max speed is equal to 4. And then basically you can go, all right, well, when I look at that, when is that occurring? So the max speed equal to 4 occurs at a time on the interval of 2 to 4 seconds. And so that would answer that question. All right. And so the idea here is you want to be very careful that when you're looking for the moving the fastest, it's kind of like you're doing this over here, but you're looking at where your absolute value, where it is the greatest distance from the x-axis, essentially. So it could be moving the fastest in the negative direction to the left, or moving the fastest to the right. In this case, it's moving the fastest to the left, and it's happening on 2 to 4 seconds. Okay. Now, we of course could do an extension on this and talk about the acceleration, but because the velocity is constant and on every section, what would be the second derivative of all this? If I said draw the acceleration graph, your acceleration graph for all of them would simply be the 0, because you're not accelerating, you're moving at a constant speed, you're moving at a constant speed, you're moving at a constant speed, you're moving at a constant speed. So the idea here is that we don't really have anything of interest to talk about with your acceleration graph. Now, what might be a typical multiple choice question, though, is I might come along and give you a velocity graph, kind of like what you have up here. Suppose my velocity graph looks something like this, where I have, maybe it comes up, comes down, comes up, and comes down. So we'll still do our seconds over here, and then now this might be inches per second, because that's a velocity graph. And they might ask, what time is this particle moving the fastest? Now, there's kind of two things that you want to look at here. You can either take your velocity graph and redraw it and say, what would my speed graph look like? The speed graph of this same function would simply be the absolute value of the velocity, and that's that transformation where you're like, hey, all the negative parts come up. So the maximum speed is going to occur at whatever this value is here at c. Okay. Another way of looking at this is trying to determine whether you're speeding up or slowing down. That's another question to ask. So if I'm looking at this, maybe in this situation, maybe at this point right here, I want to know, is the particle speeding up or slowing down? Well, what I know here is that velocity is negative at this point. And then I start thinking about, well, what's happening with acceleration? If I'm going to draw the tangent line right here, the slope of the tangent line there is a negative number. So my acceleration at that point is also negative. So they are working together. So let's call this point A. So at point A, the particle is speeding up. And so the idea is you're not looking at your velocity, you're actually talking about your speed. And then again, you can look over here at that same point at A, it's speeding up because the speed curve is increasing. But here, when you're on the velocity curve, you have to look at velocity and acceleration. If they're working together, then you're speeding up. If I look at a point over on this side, okay, I'm on my velocity curve. We'll call this point B. Is that particle speeding up at that point? Well, what I know here is that my velocity is still negative because I'm below the x-axis. I look at the slope of that. My slope is a positive slope. So that means my acceleration at that time is positive. These two things are working against each other. So if they're working against each other, the particle is slowing down. And again, another way of looking at it is once I flip the velocity curve and make it a speed graph, then I'm looking at this point right here. What's happening to my speed on this section? Speed is decreasing. Slowing down, speed decreases when they work in opposition of each other. So that's kind of giving you a little bit more background on that speed and velocity information. All right, so we're going to do example 7 here too as well in this video. And the reason why we want to look at this is because graphically they don't always have to give you a position function. Notice that what I have given you here is a velocity function that you are looking at. And so now you're going to be using the velocity function to help you answer the question. Now in this case I'm moving along a vertical line now. And the only difference with that is really what direction you're going in. We'll consider the positive direction to be moving up, and we'll consider the negative direction to be moving down. But when will the particle be moving down? Same reasoning as we had before. When your velocity curve is negative, it's going to be moving down. Now what you have to remember here is that I gave you the velocity curve. So I'm not looking at the slope of this, because the slope of this is acceleration. What I'm looking at is when is the velocity curve that I gave you actually negative or below the x-axis. So this is the portion of the curve where your velocity, v of t, is less than 0, below the x-axis. So we're changing our perspective because we have a different graph given. And so this is happening from 1 to whatever that value is. Let's just, for right now, well, maybe let's go ahead and find it while we're here. I'm going to do a little bit of extra work. This point right here is 5, 2. This point right here is 3, negative 3. And I'm sure at some point I'm going to need to find the slope of this line for this question. So my slope, which is change in y, let's do 2 minus negative 3, which is going to be 5, and 5 minus 3, which is 2. So our slope is 5 halves. The equation of that line, you know, because all these things, there are times in the AP where you're not allowed to just think hey, I'm just going to guesstimate it. My equation of this line is actually going to be a slope, 5 halves x minus 5 plus 2, and then that point right there is nothing more than your x-intercept, which is when you let y equal 0. So we would get negative 2, subtract the 2 over, 5 halves x minus 5, multiply by 2 fifths, negative 4 fifths, equals x minus 5, and then add 5 to negative 4 fifths, so 5 plus negative 4 fifths would give me 21 fifths. Okay, so that point right there is 4 and 1/5, or 21 fifths. So I add that in for use here. And so when is the particle moving down? When our velocity is negative. So we would say particle moves down for the time on the interval starting at 1. I don't include 1 because that's got a speed of 0, all right, which is stopped. So 1 to this 21 fifths, and then our open braces. And the reason, because v of t was less than 0, that we basically got from looking at the graph. Right? So now we go, when is the particle moving up? Well, the particle moves up. Again, the reasoning is the same. V of t greater than 0 that we were using before, and I gave you the velocity graph. So now we're looking for above the x-axis. So on this section, we have two sections of the graph that are above, here and here. Right? And so it's very nice we already found that value, so we would simply say particle moves up for, oh, and let's add seconds here since I have my units, t element of 0 to 1 second, and t on the interval of that 21 fifths to 6, and now I'm going to put a bracket there, and then I'm going to come back and I'm going to put a bracket here. And you might ask, well, why is she putting a bracket there? Because I'm not going to include the 1 because that's a slope of 0. That's v of t equal to 0. But what's v of 0? V of 0 is 2. That's a positive number. So it moves up if you have a positive velocity, so I'm going to include that. Likewise, over here at 6, v of 6 is also equal to 2, which is a positive number. So I want to include that. So you want to make sure that you pay attention to what you're going to include here. Because I gave you the velocity curve, you know that it's positive velocity at 0. It's a 0 velocity at 1, so I don't include it. 0 velocity at 21/5, and then a positive velocity at 6, so I want to include it. And again, our reason is because v of t is greater than 0. Now we want to know, when does the particle reverse direction? Now, two things we're going to be looking for there. It's going to reverse direction, it's going to stop when the velocity equals 0, and it has to change sign. Now, basically, because we have the graph over here, we're looking at where it crosses the x-axis and actually goes from positive to negative, and then from negative to positive. So it reverses direction in two places. Reverses direction at t equal to 1 second and at t equal to 21/5 of a second. And again, our reason is because you have to say two things. Your v of t is equal to 0, which says you stopped, and v of t changed signs. This is kind of leading to an important information that we're going to have when we start doing applications. What justification do you have to give? All right, the next question is, when is the particle moving at a constant speed? Moving at a constant speed. Now, this is where you start getting confused, because you start going, hey, the slopes of all of these are constant. But that's not what I'm looking at. The slope of this curve is acceleration. When I ask for when is the particle moving at a constant speed, we're looking for where v of t is a horizontal line. That's basically what we're looking at. When is the velocity not changing, which would be when it's a horizontal line segment. So the place where the velocity is not changing would be on this section up here. So from 5 to 6 seconds. So our velocity, particle moves at a constant speed for t in 5 to 6 seconds. Now, let's talk about kind of whether we want to include those. Now, I initially put these parentheses, but then let's think about it. What speed are you moving at 5? You're moving at 6. Oh, sorry, 2. 2 inches per second. What speed are you moving at 6? 2 inches per second. What speed are you moving anywhere in between? 2 inches per second. So I am going to go back and I'm going to include these because all of these times have exactly the same velocity, which happens to be 2 inches per second. Okay. Now, where is the particle moving at its greatest speed? Now again, this is where you have to be careful. Where you want to be careful because this is talking about the greatest speed, and you're given the velocity graph. So when you look at this, you have to remember that you're looking for the biggest speed, which is the absolute value. You don't always necessarily have to redraw it, but you have to think about this, that it's coming down, and then this section has to get flipped up, and so it will come up, and then come up a little bit more, come back down, and then come up and do our 2 like this. So our maximum speed occurs where the distance from the x-axis is the greatest, and that's going to occur at 3 seconds. So our particle is moving the greatest speed at t equal to 3 seconds, and the reason is because the absolute value of velocity, which is the speed, has the max value. So that's what you want to be careful of. Make sure that if you're talking about max speed that you actually look at the speed graph. All right, now when is speed increasing? All right, now here's our justification. You could look at the speed graph. Okay, here we go. I can see where I'm increasing in two places. Or I can think of it to say I'm looking for where the velocity is going to be positive and your acceleration, your slope, is going to be positive. But there's two cases. You're also looking at the case where your velocity is negative and your acceleration is also negative. So I'm looking for above the x-axis with a positive slope, okay? Above with positive slope, or I'm looking at below with negative slope. So that's the things that you can do. So you, instead of having to graph the speed function, what you can do is you can look here. So I'm looking for above with positive slope. Here's above with positive slope. Okay. Notice I don't want zero slope. I want above with positive slope. So this would be from 21/5 to 5. So we would say 4t on the interval, 21/5 to 5. And now let's evaluate whether I want to include those values or not. Let's see. I would not include here because I don't have a slope there, so I don't have any acceleration. Here I would not include because my velocity is not positive there. It's 0. So that wouldn't meet it. So I would not include both endpoints. But I also have to go, and for t on the interval, it is also going to be speed increasing when the velocity is negative and it has a negative slope, which would be this section right here. So that would be from 1 to 3. 1 to 3. 1 to 3. Now you can also see this on your speed graph, because if you look at your speed graph, here's my 1 to 3, and then here's my 21/5 to 5 that we're taking a look at. Okay. Now, I mean, I guess technically we might want to take out, in this 1 to 3, I do have some concerns, because right here I do not have any acceleration. There's a cusp. So let's come back in this, because you have to have both acceleration and velocity in order to be speeding up. And I'm going to break that 1 to 2, and then I'm going to do the 2 to 3. Because you have to have speed and acceleration. You have to have velocity and acceleration both being positive or both being negative for that one. Right? Now, when is speed decreasing? Same reasoning. In this one, we want v of t and your a of t to be opposite signs. Opposite signs. We want them working against each other. So I'm looking for either a positive velocity with a negative slope. There you go. Positive velocity, negative slope. So that would be my 1 to 2, or 0 to 1. 0 to 1 seconds for t in the interval, 0 to 1 seconds. And we already took care of 1 to 2, 2 to 3. So now let's look at 3 to this 21/5. 3 to 21/5 right here, it has negative velocity, but the slope's positive. So they're working against each other. Okay. And t in 3 to 21/5 seconds. Now again, you could look at this on your speed curve and be like, hey, speed decreases here and here. And that's a little easier when you have the graph. I'm kind of emphasizing this because if I was in the graphical or the numeric representation, I'd have to make sure I take a look at that. All right, and it says graph the acceleration where defined. So we have constant acceleration because these are all linear slopes, but remember, cusp would be not differentiable, which means there's no acceleration at 2, no acceleration at 3, and no acceleration at 5, and at the endpoints because we don't have a left and a right. So when I go to graph my acceleration function, let's see, did I find all the slopes I need up here? I know the slope on this section is 5/2. Let's find the slope here because that's our acceleration. This point was 2, 2. 2, negative 2. And so I went basically over 1, down 1. My slope is 1. And then here I'm going from 0, 2 and to 2, negative 2. So my slope would be negative 4 over 2 or negative 2. So I go down 2 over 1. So I have a slope of negative 2 first. So negative 2. And I'm doing that for the first 2 seconds to there. Then I have a slope of negative 1 until I get to 3 seconds. Right. Oops, I should say negative 1 there. Then I have a slope of 2.5. So 2.5 all the way until I get to 5, and then from 5 to 6 I'm constant, so I have a slope of 0. And the slope of the velocity curve is my acceleration. Right? And when is acceleration the greatest? Acceleration is the greatest for t on the interval from 3 to 5. Alright, so this is a video. This kind of wraps up our video talking about looking at the graphical perspective in particle motion and determining the answers from the graphs.